Okay, so Bode plot. It is not always easy to get a quick plot of the magnitude and phase of the transfer function as we have seen in the previous video. That is, you will have to change the value of omega 1, 2, 3, 4, 10, 20 and so on to plot the frequency response. It's not easy. Actually, a more systematic way of obtaining or plotting the response is to use a Bode plot. Okay, so instead of having to key in the value or calculate the value of the magnitude and phase one by one, 1, 2, 3 omega, 10 omega and so on, it's better to use Bode plot. Okay, so before we get to construct Bode plots, we should take care of two important issues: the use of logarithm and decibels in expressing gain. Okay, so these two are important in order for you to plot using Bode plot method. Okay, because Bode plots are semi-log plots. Semi-log means that one exists in log scale and one exists in linear scale. Okay, so we plot the magnitude in decibels, okay, in decibel, in dB, and phase in degree unit of a transfer function versus the frequency. So in other words, the Bode plot, this is the frequency, this is the magnitude in decibel, right? And the frequency or what y-axis in log scale, this will be in linear scale. All right, these Bode plots are based on a logarithm. It's important that we keep the following properties of a logarithm in mind. That is, if we have a two value multiplication of two values, and in log is similar to log each value individually and then add them together, right? This is if these two values are multiplication of each other. Okay, p1 times p2. So if p1 over p2, we log the value, it is actually equals to log p1 minus log p2 if we separate them. Okay, then log pn equals to n log p, and log 1 is 0. So you can try this in your calculator. Log 1 is 0. So in a communication system, gain is measured in bells. Historically, that the bell is used to measure the ratio of two levels of power or power gain. That is, G, the gain, equals to log 10 of P2 over P1. Alright, so gain is log 10 log 10 P2 over P1. Okay, gain in decibel is equals to 10 log 10 P2 over P1. Alright, alright, so never mind, let's just go straight to the Bode plot. How to plot using Bode, how to plot the transfer function using Bode plot method, right? So basically, a transfer function may be written in terms of factors that have real and imaginary parts. Okay, one such representation might be like this. Alright, h omega transfer function, and the transfer function, the component of the transfer function, the numerator and denominator can be in general represented like this. Okay, right, of course this looks confusing, but if we replace j omega with s, as in the previous video, we can see that this is much more easier to read or to see. Okay, if we replace j omega with s, right? We will do that later. So here, this representation is called the standard form. Okay, so the transform function may include up to 7 types of different factors that can appear in this combination. We'll look later. Oh, sorry, we have the factors here, right? 7 types of different factors. Okay. One. Okay, the first factor is gain k. Okay, k is the gain. Okay, this is the first factor, which is this. This is the first factor, which is called gain. And then we have pole, which is represented by, if we change this j omega with s, then pole is actually 1 over s, right? Or 1 over j omega. That is the second factor, which we call pole. So in this case, pole is this, if the value is -1, right? And 0, next is the third factor is 0, alright, j omega, or you can replace it with s, s with power of plus. Okay, so this is also a 0, but it must be a positive power. Alright, so basically if s is at the top, then it is called 0, but if s is at the bottom, it is called pole. Alright, because this is s minus 1 is equals to 1 over s. Right, so if s at the bottom, it is called pole. S at the top, it is called 0. Alright, so there we have 3 factors, 1, 2 and 3. Next is simple pole. Okay, we know that pole is 1 over s. Okay, next is simple pole. Simple pole is actually 1 over 1 plus j omega over p1, right? Or this one, 1 over 1 plus j omega over p1. So this is simple pole. And then if we have simple pole, we have simple 0 as well. So 0 is located at the top, pole is located at the bottom, right? So we have 1, 2, 3, 4, 5, and then 6 and 7. So we have quadratic pole, okay, which is this one, quadratic pole, and then we have quadratic 0, right? So again, we have the gain, we have a 0, which is positive, pole, which is negative, simple 0, which is this, simple pole, which is this, quadratic 0 and quadratic pole. So you can see that the pole is at the bottom, 0 is at the top. That is just the name, right? So in constructing a Bode plot, first we need to know that these 7 factors. Okay, then once we have identified the factors, we have to plot or draw the curve for each factor separately, and then finally we can add them all together. Alright, so this is the method of constructing a Bode plot. We have to draw each factors individually on the piece of semi-log graph paper, and then finally add them all together. Okay, what do I mean by drawing each factor individually? Okay, this is, let's look at the first factor. The first factor is gain k. Okay, in k is the first vector. So the magnitude is 20 log 10k. So this is you have to remember this, 20 log 10k. So for magnitude plot, 20 log 10k is looks like this, a straight line. And for phase plot is also a straight line, but at 0. Okay, so if we have k value, for example like 20 for example, so you have to do calculation. 20 times log 10 20, for example, what is the value? Let's say 20 dB here. So you plot 20 dB, a straight line from 0.1 to 100 and so on. Okay, it's a straight line to infinity. Same thing is a straight line to infinity, but in this case the phase is 0. So that is how you plot the first vector. Okay, so we have the first vector, which is gain. Okay, depends on the value of the gain, then you can plot the magnitude plot and phase plot of the vector k. Right, this is the coding to plot the first vector. Let's look at the second and third vector, which is pole and 0. Okay, we have pole and 0, which is just a simple s and 1 over s. Okay, so for 0, okay, for 0 it is a straight line like this, crossing at 1 omega. Okay, straight line like this, crossing at 1, and this is 0 here, and the slope is at 20 dB per decade. Okay, the slope is 20 dB per decade. So what is 20 dB per decade? So the slope, if you remember, the calculation of the slope is, if we have y, x, slope is equals y over x, isn't it? That is the equation for the slope. So in this case, the slope is, if you look at here to here, that is 1 decade. Okay, so from here to here, that is 1 decade. So you need to fully understand this. Why is it called 1 decade? Because 0.1 times 10 or decade is 1.0. So here to here is 1 decade. From 1 to 10 is another decade, 1 decade. 10 to 100, okay, not 10 to 20, but 10 to 100, that is 1 decade. 100 to 1000, that is another decade. All right, so here to here is 1 decade. Okay, so we know that from here to here is 1 decade. Now here to here is 20 dB. Here to here is 20 dB. Right, so we have 20 dB over decade. So this is the slope, 20 dB over decade. All right, so this is for 0. Okay, this is for 0. Going back to for 0, which is s, is straight line like this, crossing at 1, and don't forget the slope, 20 dB per decade. That is for 0. Now let's look at the pole. Now for pole, okay, sorry, I don't have the pole here. Let me just skip to the, all right. So this is the 0, right? Remember, cross at 1, 20 dB per decade. So for pole, which is 1 over s, it is the inverse, still crossing at 1, but the slope is now negative 20 dB per decade. So 20 dB per decade, but it is now in negative slope, going down. Okay, negative slope. This is positive slope, this is negative slope. And don't forget the phase plot. The phase plot is, so for 0 it is 90 degree, straight line 90 degree, but for pole it is negative 90 degree. Okay, yep, so you can see your phase is negative 90 degree. And this is the coding, MATLAB code for plotting the second and third factor, the 0 and the pole. And let's look at the fourth and fifth factor. Okay, so fourth and fifth factor is the simple pole and simple 0. Simple 0 and simple pole. So simple 0 is 1 plus s over z1. Simple pole is 1 plus s over p1. Okay, so let's just refer to this table because it's a summary. It's a summary for all factors. Okay, so we have 0, we have poles, we have simple 0, we have simple poles. Let's look at simple 0. Simple 0 is 1 plus s over z. Okay, so here how to plot simple 0. It is a straight line at 0 dB, right? Straight line 0 dB, and when it reach z, it will start increasing 20 dB per decade, right? 20 dB per decade at z, right? Z. Okay, same thing for simple pole. At 0 dB, it's a straight line until it reach at P. Okay, at P, then after that it will start decreasing or declining 20 dB per decade, right? So n here means that if it's a power of 2 or power of 3, you just have to multiply with 2 or 3, multiply with n. So for example, if n is 2, so this will be 40, then this will be 40 dB per decade. Instead of 20 dB per decade, it is now 40 dB per decade. Alright. Okay, simple 0, simple pole. That is the magnitude plot. Now let's look at the phase plot. Simple 0, phase plot is, we have 0 degree. Now here is z over 10. Okay, and then it will increase until 10 times z. So this is 2 decades, right? This is 2 decades. So here z over 10 increase until 10 times z, and then going back to straight line, and the value here is 90 degree. Okay, from 0 to up here, here to here, that is 90 degree. 90 degree. Okay, so in other words, here to here is 45, here to here is 45 degree. Okay, so here we can say that it is 45 degree per decade. Okay, 45 degree per decade. 45 degree per decade, because here are 2 decades. Okay, so same thing for simple pole, just the reverse. Okay, instead of 45 degree per decade, this is negative 45 degree per decade. Okay, so for quadratic pole and zero, I will skip this.